In the previous section, we learned the definition of the limit of a function. And in section 2.3, we are going to be calculating limits now using what are called limit laws. Essentially, these laws can be proven to be true by just using the definition of the limit of a function from section 2.2, but these laws will make our life a little easier when we are actually calculating limits. So first, we start with some basic limit laws. You can find these in the e-textbook. Suppose that c is a constant and that the limits, limit as x approaches a of f of x and limit as x approaches a of g of x exist. Then, 1, the limit as x approaches a of the quantity f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Very similar to this, number 2, the limit as x approaches a of f of x minus g of x is equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. These first two are just called the sum and the difference laws. And you can think of it as essentially just distributing the limit across the sum or the difference. Number 3, the limit as x approaches a of a constant c, remember c is a constant, times f of x is equal to the constant c times the limit as x approaches a of f of x. That's just the constant multiple rule that we can refer to, constant multiple, and essentially we're factoring out the constant. You could justify why this is true by just thinking that a constant times f of x is just adding f of x a multiple number of times, so over and over and over. So you can just use the sum law to essentially prove the constant multiple law. And then 4 and 5 involve a product in number 4 and a quotient. And essentially we can distribute the limit through those as well. So for example, in number 4, the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. And then similar to that, number 5, if we have a quotient, f of x divided by g of x, and we are taking the limit as x approaches a, then this gives us a new quotient, the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. And this is, of course, if the limit of g of x as x approaches a is not equal to 0. If it was equal to 0, then this would mean that this limit does not exist. Or we might have to do some sort of simplification like we saw in the previous section. So with those laws, let's look at a few examples. So number 1 from page 102 of the book, and we're just going to look at parts B and D. There's some other ones in here that you can certainly practice on your own. So part B says we want to find the limit as x approaches 2 of g of x to the third power. And what we've been given is that the limit of g of x as x approaches 2 is equal to negative 2. So the way that we can figure this out is remembering that powers means the same thing as repeated multiplication. So instead of g of x to the third power, it's just g of x times g of x times g of x. Then this gives us, distributing the limit across that product, the limit as x approaches 2 of g of x times another limit as x approaches 2 of g of x times a third limit as x approaches 2 of g of x. This just gives us negative 2 times negative 2 times negative 2. Which just gives us negative 8. Part D, let's use some room over here. Here I only need the limit of f of x and the limit of g of x for this. The limit of h of x was given for other problems, so if you want to go through some of those, you can use all 3 of them. But for part D, the limit as x approaches 2 of 3 times f of x divided by g of x. The first thing that we can do is use the quotient rule, which allows us to put our limit in the numerator and the denominator, provided, of course, that the limit as x approaches 2 of g of x is not equal to 0, which is true. We were given that it actually equals -2. And also in the numerator, we can see that we can factor that 3 out of that limit. So what we have is 3 times the limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x, which, since we know those limits, they exist and we have the numerical values for them, this gives us 3 times 4, because that's the limit of f of x as x approaches 2, divided by -2, which is 12 divided by -2, or -6. So instead of doing a graph, instead of plugging in some numbers that get close to 2 and seeing what the functions are equal to, if we know the values of these limits, then we can just use those to find new limits. In one of those examples that we did, part B, we can see that the product law can lead to a law involving powers. It's pretty straightforward, as it follows from the product law, and this is very similar to the constant multiple law. So in this case, number 6 is another law that we can remember. The limit as x approaches a of f of x to the nth power is the same thing, or is equal to, the nth power of the limit as x approaches a of f of x. And that's essentially what we did in part D. We really just took what we knew, the limit of g of x as x approaches 2 equals -2, and raised it to the third power, which gave us -8. So that's a law that would have sped up part B above. And then this law says when n is a positive integer, we will see that if you combine this with the quotient rule, quotient law I should say, you can actually then use a negative integer, because that would just turn into division. And then we will also see that this was really true for real numbers. But the way they have this organized just takes us through this step by step. And then here's 2 other straightforward limits. Number 7, the limit as x approaches a of a constant c is just equal to c. And the way that you can understand this is just by considering what a constant function looks like. If you were to have a function y equal c, it would just have a graph of a horizontal line. As you are approaching a value a, so as x is approaching a, anywhere on this horizontal line, the value of the function is always c. So no matter where a is, you will always be approaching c as the value of that limit. And then very similar to that, number 8, the limit as x approaches a of x is equal to a. There's another graph that we can do for that one. If you were to remember that the function y equal x is just a diagonal line with slope 1 that goes through the origin, anywhere along that curve, as far as an input, you would get out the exact same output. Plug in a for x, you get a back out for y. So as you are taking the limit as x approaches a from either the left or the right, the value of the function is also approaching a. So that's why we have the rule for number 8. And then taking further combinations of laws, we get numbers 9 and 10. The limit as x approaches a of x to the n is equal to a to the n, where n is a positive integer. This is just a combination of rules 6 and 8, or laws 6 and 8 above. And then number 10, the limit as x approaches a of the nth root of x is equal to the nth root of a, where n is a positive integer. Right here you can see that we're talking about roots. When n is a positive integer, this is already giving us fractional powers, which is what I was referring to earlier. When we have fractional powers, these limits will still work. And here this is saying if n is even, we assume that a is greater than 0. Of course, we're sticking with real numbers is what that's saying. And then one final law, which is a generalization of the previous law. So this is sort of a combination of 6 and 10 together. The limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x. And here again, if n is even, we assume that the limit of f of x as x approaches a is positive. So let's use some of these laws for some other examples. So example 2 from page 97 of the book, let's start with part A. The limit as x approaches 5 of the polynomial 2x squared minus 3x plus 4. So first thing that I can do is I can distribute the limit across the sum. That's just going all the way back to the sum law that we saw, which was the first law that we looked at. So we would get the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x, and then plus the limit as x approaches 5 of 4. And in fact, you can see I've even used the difference law that we saw. So then I have some constants with some of these. So on the first one, I can factor out the constant of 2, which gives me 2 limit as x approaches 5 of x squared, and then minus 3 times the limit as x approaches 5 of x, and then plus the limit as x approaches 5 of 4. So now in my first limit, I'm going to use rule number or law number 9, where I have a power of x. So this just becomes 2 times 5 to the second power. So here I used law 9. And then in the next limit, this is just going to turn into 3 times 5. Here I've used law number 8. And then on the last limit, that's just a constant function, 4. So this just gives us 4, and that's using law number 7. So then this all amounts to 2 times 25, so 50 minus 15 plus 4, which is 39. All right, so now let's look at part B. Here we have the limit as x approaches negative 2 of the rational function, x cubed plus 2x squared minus 1 divided by 5 minus 3x. And again, we can start with the quotient law, which just says we can distribute the limit to the numerator and denominator. So limit as x approaches negative 2 of x cubed plus 2x squared minus 1 divided by the limit as x approaches negative 2 of 5 minus 3x. Now all we have in the numerator and denominator are polynomials. So these actually fall just like we did in part A. I'll have distributing across the sum and difference in the numerator, the limit as x approaches negative 2 of x cubed plus the limit as x approaches negative 2 of 2x squared minus the limit as x approaches negative 2 of 1. And then in the denominator, I just have a difference. So the limit as x approaches negative 2 of 5 minus the limit as x approaches negative 2 of 3x. So now I'll do any factoring out of constants that I need to do, but I can also speed a couple of things up here. In my numerator, the limit as x approaches -2 of x cubed, we already know now by the power law that we saw, this just will turn into -2 to the third power. And then the second limit, I'm going to factor out the 2. So I get 2 times the limit as x approaches -2 of x squared. And then the last limit is just the limit of a constant. So I'm going to say the limit as x approaches -2 of 1 is just 1. And then in the denominator, the limit as x approaches -2 of 5 is just 5. And then I'll factor out the constant of the second limit. So I have 3 times the limit as x approaches -2 of x. So then finally, in my numerator, -2 to the third power is -8. And then plus 2 times, here I can use the power law again, plugging in -2 for x squared. So this just gives me -2 squared, and then -1 divided by 5 minus 3 times -2. So I get -8 plus 8 minus 1 in the numerator, and then I get 5, that'll be plus 6 in the denominator, and I just end up with -1 over 11. Now that we've gone through those two examples, we actually have a property that we can name from this. I took the limit of a polynomial in part A, and then I took the limit of a rational function in part B. The direct substitution property, which you can find on page 97 of your book, follows from this example. And it says, if f is a polynomial or a rational function, and if a is in the domain of f, then finding the limit as x approaches a of f of x really just amounts to plugging in a into the function. Remember, with polynomials, the domain is all real numbers, so you'll never have a problem with doing this. But with rational functions, we do have to consider when the denominator is equal to 0, and just make sure that when we're taking the limit, that value is actually in the domain of that function. These kinds of functions, polynomials and rational functions, are called continuous at a, as long as a is in the domain of the function. And we can always use the direct substitution property for these functions. But not all functions can use the direct substitution property. So in particular, not all rational functions can do that. So in fact, an example that we saw before, which came up in section 2.1, find the limit as x approaches 1 of x squared minus 1 divided by x minus 1. We can't plug in 1 to this function because 1 is not in the domain of our rational function. So we can't let x equal 1. It's not in the domain. However, we can simplify. We can say the limit as x approaches 1 of x squared minus 1 divided by x minus 1 is the same thing as the limit as x approaches 1 of x minus 1 times x plus 1 divided by x minus 1. And now I can actually simplify my numerator and denominator by canceling out a common factor. And this leaves me with the limit as x approaches 1 of x plus 1. And now we have a linear function, which is a polynomial, and I can just direct substitute in 1. So I get 1 plus 1, which is 2. So what we just did is replace one function with a simplified function that was the same thing as the original function. And then we used this fact. If two functions are equal, if f of x is equal to g of x, when x is not equal to a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided the limits exist. So what we did was we started with taking the limit of a function f of x, we simplified it, and we got a new function x plus 1, which was exactly the same as our original function f of x everywhere except at 1. And then we can actually take our limit of g of x, which was just x plus 1, and get an actual solution. So now let's look at another example that uses this fact that we just pointed out. This again comes from our book, number 32, on page 103. We would like to find the limit as h approaches 0 of this function, which is a rational function, 1 over x plus h quantity squared minus 1 over x squared, all divided by h. First thing to notice, even if this is a rational function, you cannot necessarily use the direct substitution property if the value that you are taking the limit as your independent variable approaches is not in the domain of the function. So in this case, if h is approaching 0, if I plug 0 in for h, I get a 0 in the denominator, which is not allowed. That's not in the domain. But something else that I want to point out is if h is equal to 0 in that expression, I get 1 over x plus 0 quantity squared minus 1 over x squared, all divided by 0. And what this turns into is 1 over x squared minus 1 over x squared, which is 0, divided by 0. And this is actually something that is important to point out. If you ever reach with a rational expression 0 over 0, this actually tells you that you can do some simplification and essentially cancel out some common factors. This is exactly related to an example we saw earlier when we had x squared minus 1 divided by x minus 1. There was a hole essentially in the graph. So this is the case that we have here. So what we have to do is take a function and rewrite it as something else so we can actually take that limit. So the way that we're going to do this is just by taking a look at our expression 1 over x plus h quantity squared minus 1 over x squared divided by h. And I'm going to combine the terms that are in the numerator. And I'll do that by just using a least common denominator. So in this case, I'm going to multiply the first fraction by x squared over x squared. And then the second fraction I'm going to multiply by x plus h quantity squared divided by x plus h quantity squared. Now I have a common denominator, which is x squared times x plus h squared. And then the numerators will just be x squared times 1, which is x squared, minus x plus h quantity squared. So now let's further simplify by combining those terms in that numerator by first expanding x plus h quantity squared. So I get x squared minus x squared plus 2xh plus h squared. Make sure you keep that in parentheses because you have to then subtract all of that, divided by x squared times x plus h quantity squared. And that was this complicated numerator that was all being divided by h. But now to also make this a little bit easier, instead of dividing by h, remember dividing by something is the same thing as multiplying by the reciprocal, which would be 1 over h. So now what I actually have is in the numerator x squared minus 2xh minus h squared, all divided by h times x squared times x plus h quantity squared. The x squared terms will cancel each other out, and what I'm left with is negative 2xh minus h squared divided by h x squared times x plus h squared. So now the next thing that we can do is notice that we have a common factor of h in the numerator. I'm going to factor that out. H times the quantity negative 2x minus h divided by h x squared times x plus h quantity squared. And since I have a common factor of h in the numerator and denominator, they divide each other out. And now I'm left with a simplified version of what we started with. Negative 2x minus h divided by x squared times x plus h squared. And here I want you to notice, if you were to plug in 0 for h, that would be okay. You would get negative 2x in the numerator, and you would get x squared times x squared in the denominator. So we can actually now take this limit. So what this means is if I go back to what I had started with, the limit as h approaches 0 of the expression 1 over quantity x plus h squared minus 1 over x squared all divided by h. That's now the same thing as the limit as h approaches 0 of this new expression that I got, with all of my work proving that those two things are equal. And now I can use direct substitution, which just means plugging in 0 for h. So I don't need to write the limit notation anymore. All I have to do is just replace h with 0. And this leaves me with negative 2x divided by x squared times another x squared, so x to the fourth. I can cancel out a common factor again of x, and I'm just going to be left with negative 2 divided by x cubed. So at this point, I actually want to point out what we just did in this example was take the derivative of a function, which is not something that we've learned yet, but it is going to be coming in this class, learning how to take derivatives. And so this process of learning these limits, this is why we are doing this, because part of that definition will be taking a limit of what's called a difference quotient, which is the function that we actually started with. And so we have to go through the practice of learning how to rewrite those difference quotients into something simplified that we can then use direct substitution to then evaluate the limit. So another example similar to that, this is example 6 from page 99 in the text. Find the limit as t approaches 0 of the expression square root of t squared plus 9 minus 3 all divided by t squared. And again, if you were to plug in 0 for t, you would get the square root of 9, which is 3, minus 3 in the numerator, and 3 minus 3 is 0. And in the denominator, you would get 0. So again, we have a 0 divided by 0 form. So can we simplify or change this first? And we can. If you take square root of t squared plus 9 minus 3 divided by t squared, you can do what's called rationalizing, not the denominator, but the numerator, by just multiplying by t squared plus 9 plus 3. And what this will do will simplify what we have so that we can then actually evaluate the limit. So if I use the FOIL method, in the numerator, I get the square root of t squared plus 9 times the square root of t squared plus 9. When you multiply a square root of something times itself, that's essentially undoing the square root. So I'm just left with t squared plus 9. And then when I multiply the square root of t squared plus 9 times positive 3, and also the square root of t squared plus 9 times negative 3, those two terms will cancel each other out because one is positive and one's negative. And so then all that's left is just negative 3 times positive 3, which is negative 9. And so what we actually end up with is just t squared in the numerator. And then in the denominator, I have t squared times the quantity square root of t squared plus 9 plus 3. Those t squared terms will cancel out, by division. I'm left with 1 in the numerator. And so what I actually find out is that the expression I started with is equal to 1 divided by the square root of t squared plus 9 plus 3. And so now I can evaluate my limit. The limit as t approaches 0 of what we started with, square root of t squared plus 9 minus 3 divided by t squared, is now just the same thing as the limit as t approaches 0 of my new expression, 1 divided by the square root of t squared plus 9 plus 3. I can use direct substitution because when I plug in 0, I just get the square root of 0 plus 9 plus 3, which turns into 1 divided by 3 plus 3, or 1/6. Both of those examples that I just looked at are examples of this fact, that you can replace a function with another function, and you want to do that if, in that simplification process, you can then take the limit. Now I want to look at example 9 from page 100. This is serving as a good review of what we had seen in a previous section. We want to find if the limit as x approaches 4 of f of x exists, where f of x is equal to a piecewise defined function. It's equal to the square root of x minus 4 when x is greater than 4, and it's also equal to 8 minus 2x if x is less than 4. So we have two parts to this. And what we want to think of is, if we're approaching 4, we have essentially a left and a right side of this function. The left side would be when x is less than 4. The right side would be when x is greater than 4. So we're actually just going to find the left and right hand limits. So the limit as x approaches 4 from the left of f of x, that's really now just using the function that's defined for all the values x that are less than 4, which becomes 8 minus 2x. And so now this left-hand limit of f of x becomes just the limit as x approaches 4 of 8 minus 2x. Notice I've replaced the function with just the piece that is to the left of 4. And now I can evaluate this by just acting as if x is approaching 4. It's a linear function, so it's just direct substitution. 8 minus 8, which is 0. And then if we look at the limit as x approaches 4 from the right of f of x, now we can replace f of x with the function that it's equal to for all values to the right of 4, which is the square root of x minus 4. And then just look at the limit as x approaches 4. Here we can bring the limit inside of the root. That's one of our laws that we discussed. And then what's inside is just a linear function again, so I can use direct substitution, which gives me the square root of 4 minus 4, which again is 0. So since the left and the right hand limits are equal, then by what we learned in section 2.2, the limit does exist. So we would say yes, and the limit is 4. Oh, sorry, not 4, 0. All right, so then finally, to end this section, a couple of theorems that complete a lot of these laws that we looked at. This is the end of all of the laws, and these theorems are a culmination of some of those things, but also give us some other tools besides the laws that we had. So first, if f of x is less than g of x, when x is near a, except possibly at a, and the limits of f and g both exist as x approaches a, then the limit as x approaches a of f of x is less than the limit as x approaches a of g of x. Essentially, if the functions have an inequality relationship, then so do the limits. This then leads to a more powerful version of this theorem called the Squeeze Theorem. Here, if you have three functions, f of x less than or equal to g of x less than or equal to h of x, where x is near a, except possibly at a, and if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, which is equal to a value L, then that squeezes the limit of g of x as x approaches a to be L. Essentially, if you have a function on top, h of x, and then some other function on bottom, like f of x, and if they're both approaching some value, then whatever your g of x is, if it's between those functions, it's going to be approaching that same limit at a certain point. Let's see how that is used in this last example. Example 11 from page 101. Show that the limit as x approaches 0 of x squared sine 1 over x is equal to 0. So first, we can't use the product theorem or the product law because the limit as x approaches 0 of sine of 1 over x does not exist. We actually discussed that in section 2.2. So we can't use the product law because you need those limits to exist. If I used direct substitution, I'm not allowed to do that because sine is not a polynomial or a rational function. So first, I'm going to use the idea of what happens to sine of 1 over x. So if we recall, as x approaches 0, 1 over x approaches infinity. And that means that sine of 1 over x has no limit. It just oscillates between -1 and 1. So that's what we saw in section 2.2. The limit doesn't exist for sine of 1 over x as x approaches 0 because it just never stops going up and down between -1 and 1. But this actually gives us a fact. The function sine of 1 over x is between -1 and 1. And now we can actually use that because this is looking like the squeeze theorem. I want to take a look at when a function is between two other functions. So now I need one more piece in there, x squared. That's easy. I'm just going to multiply everything in here by x squared. So I would have -1 times x squared less than or equal to x squared times sine of 1 over x less than or equal to 1 times x squared. I'm allowed to do that with this inequality because multiplying by x squared is always guaranteed to be multiplying by a positive. So now what I have is x squared sine of 1 over x is between -x squared and +x squared. So now we have our functions that showed up in the squeeze theorem. F of x is -x squared, h of x is +x squared, and g of x is the one that's in the middle. Now let's look at the limits. The limit as, in this case, we're using x approaches 0 of f of x, meaning our lower function, is just going to be, that's a polynomial, negative quantity 0 squared, which is 0. And the limit as x approaches 0 of the greater function, x squared, is also just 0 squared, which is just 0. So then our function x squared sine of 1 over x is in between those. Which means by the squeeze theorem, its limit gets squeezed down to 0 as well. And that answers the question. The limit as x approaches 0 of x squared sine of 1 over x is equal to 0.